Hardware to Save a Planet explores the technical innovations that are giving us hope in the fight against climate change. Each episode focuses on a specific climate challenge and explores an emerging physical technology solution with the person bringing it into reality. I'm your host, Dylan Garrett. Hello and welcome to Hardware to Save a Planet. Today's episode stretches the definition of hardware in a way that I really love. Our guest, Dr. Ye Tao, is the founder and executive director of MEER. That's MEER, which stands for Mirrors for Earth's Energy Rebalancing. He's focusing on a solution that's so simple from an engineering perspective that its potential to scale and potential for near-term impact is huge. By putting reflective materials on roofs, he's cooling individual homes, which provides an immediate increase in resilience to climate change for families in the most impacted parts of the world. And as his solution scales, it could have a meaningful impact on global temperatures. I do have to admit, when I first heard about it, it sounded a little crazy, but as I've gotten to know Ye and his mission better, I'm convinced that this is a solution more people should be talking about. To introduce Ye quickly, he has a PhD in chemistry from MIT, and he completed the research requirements for a second doctorate in physics at ETH Zurich. He decided not to defend that second doctoral dissertation, though, so he could move to Harvard to lead a lab developing microscopes for use in nanoparticle research. So despite the simplicity of his solution at MEER, he clearly has an enormous capacity for complex technical subjects, which makes me really excited to hear how he landed on this path to focus on in particular. Yeah, it's an honor to have you on the show. Thanks a lot for joining.
Thank you for inviting me. It's an honor to be here.
So first, I just wanted to set the stage for our listeners a little bit. Can you describe where you are right now?
Right now, I'm located in West Africa in a country called Sierra Leone. I think most people know the name Freetown, which is capital of Sierra Leone, because it was in the news a while ago because of the civil war, and then the Ebola outbreaks. And then recently there is a climate catastrophe, including landslides. So that people generally know Freetown through these rather negative lens. But the reason why I chose to come here is also because we project that global economy is not on a upward slope. Conditions will be pretty bad everywhere. And if a solution, as you call it, were to work in the future of a energy material scarcity, it has better to work under the most difficult conditions, socioeconomic conditions. That's one of the reasons that we motivated our choice of Freetown. And also it's in a tropical climate, and people here are definitely suffering from extensive heat waves. We can talk about that later. But before going further, I want to just correct one thing. You have mentioned the word solution. I don't think that what we work on is a solution. And I don't pretend, and I would be triggered if people tell me that they... I think I would be quite triggered if I were to hear the word solution this late in the game. I think generally when you talk about solution, it's as if we can continue this set of habits without sacrificing anything and continuing to indulge in our excesses. I don't think it's possible at this late in the game. So what I envision our approach is rather a toolkit that enable or helps the transition of the civilization to a more sustainable one. So it's rather a set of low-tech tools to help facilitate that transition, which is inevitable.
So the word solution implies that we will solve climate change or reverse the effects of global warming. And if I hear you right, you're saying it's too late for that. This is a toolkit to help us live more sustainably with the given of global warming.
More or less, because global warming is only one of the many symptoms of a much larger structural problem. There's also resource depletion, ecosystem collapse, and also the horrors that we're witnessing every day now on TV in Gaza. But if you travel outside of your middle-class suburb, you see the same thing everywhere in the world. And in Freetown, it's all the more visible. So I don't think climate change is the only challenge that we have. We're at the crossroads, and it's conglomeration of different crises, right? People call it polycrises. And we have to understand that climate change is, well, it's a big one. It's perhaps the major one. but it's a symptom nevertheless.
So I'm excited to get into more about MEER and the toolkit you're developing or you're deploying. But I wanted to touch on the origin story a little bit because, as I said in the intro, before you started MEER, you were working in a lab on nanoparticle research. You have doctorate in chemistry and have done all this deep physics research. From the outside, MEER feels like a big pivot from that. What happened?
Well, yes, like the things we were doing were quite on a different scale. So one project that we developed at Harvard, which sadly we don't have the time to really write up and publish, involved creating a very precise machining method using electron beam. So my lab was doing a whole range of things. The institute regularly invites scientists at the cutting edge of different areas to come give talks and interview, and some of them we recruit to be our colleagues. And I think the second year when I was at the institute in 2017, there was an interview that really struck me. It was about how potentially to use phytoplankton, I think, as a way to capture carbon and as a solution to global warming. And during that talk, I was looking at these future projections of temperatures and CO2 trends. If those were correct, it's quite obvious there's no way for ecosystems to survive those kind of future temperature projections. So I looked into the subject myself and started to also watch YouTube videos and search climate change related material. And then I ran into the major science communicators in this area, including Professor Guy McPherson, who still is like the person who predicts near-term human extinction as a result of these ongoing and the future trends. So without going into the quantitative accuracies of the various projections, I looked into the literature for myself, spent a year or two reading thousands of scientific papers across different disciplines, from psychology to ecology to climate science to engineering, to really try to understand what are the likely pathways for the future. And when you look at experimental evidence of how sensitive ecosystems are to even minute perturbations to the environment, temperatures of 1 or 2 degrees Celsius, constant increase rather than extreme temperature increase, almost everything we've measured have been seen to undergo local extinction or extirpation. And when you have keystone species disappearing from your local environments, that would have cascading impact on your whole ecosystem. So ecosystems will become simpler, and when certain key functions are destroyed, the whole ecosystem can come down. So those mechanisms are very worrying, and people in those fields really, in general, fear the impact of climate change much more than people looking at only temperature increase or the physical aspects. So I think it's mostly the ecologists who are most worried about this. And I was reading also in those fields, and also fishery as some sort of ecological field, projection of fishery collapse by mid-2030s, 2040s. And if we look at the data, pretty much we're on track to see like the ocean without
fishery collapse.
Fishery collapse.
That's like 10 to 15 years.
Yeah, that's the time scale. And you can prolong that by maybe 20, 30 years if we stop the fishing pressure. But the thermal impact in combination with the exploitation, the rate of exploitation humans are imposing onto the stocks together is projecting collapse by the 2030, 2040s. So taking all that together, and I did also my own analysis of paleoclimate relationship between temperature and CO2. And if we used that relationship to extrapolate ongoing emissions, it's quite clear that by roughly 2-3 years, and then by well before 2050, we would have surpassed a 2 degrees Celsius warming mark. And that's not taking into account one aspect that I believe Guy McPherson was the first to really make public, which is the aerosol cooling component, which is something that we don't directly measure, but its magnitude is very important for an accurate projection of the future pathway of the climate. And more recently, Dr. James Hansen and his colleagues wrote this paper called The Global Warming in the Pipeline. They predict that indeed the Earth system is much more sensitive to the CO2 warming that we historically observe, in part because of this aerosol component, which in previous reports by the IPCC and previous academic papers have been hugely underestimated. So in essence, the amount of CO2 warming that's in stock is much higher than what we previously understood it to be. So as a result, what we call locked-in warming is a very significant part of the equation that has to be taken into account.
What is the aerosol effect you're talking about?
Oh, the aerosol effect is due to essentially air pollution.
Okay.
During a smoggy day, for example, you can see everything is very hazy. And the reason why it's very hazy is because these nanoparticles, microparticles in the air, as a result of the pollution, is scattering light and redirecting some of the light to your eyes. So when you burn fossil fuel, you don't only emit CO2. There's a whole range of things, including nitrogen oxides, or NOx, which is composed primarily of NO2, and NO. NO2, I think, is the major component, but then they are in dynamic equilibrium in the atmosphere, meaning they can transform to each other. And one of the other chemicals involved in process is ozone. So ozone pollution is in part because of the emission of NOx, and when it's produced near urban centers, it's one of the mechanisms towards toxicity and the health impacts of ozone. There's also unburned fossil fuel, so organic components, volatile organic components. And these, under the oxidative action of ozone and other oxidizing agents, can form radicals, and they can polymerize essentially in air to form larger particles, nanoparticles. And then some of them can also condense water droplets to form clouds. So there's two mechanisms by which they can induce cooling. One is these nanoparticles formed from these photochemical reactions can directly scatter light. Part of light coming down will be scattered backwards into space. So that's called aerosol direct effect. And secondarily, they can also interact with water vapor, nucleating clouds, making clouds wider, or actually creating clouds under some conditions where they wouldn't exist because they facilitate the condensation of molecular water into the nano droplets. So the secondary cloud effect also reduces the amount of sunlight that's received at Earth's surface. So that's another cooling impact.
Okay, so you're saying, if I'm understanding you right, our pollution is actually helping to cool the Earth.
Correct.
Through these effects that you're describing.
Yeah, we can actually quantify that.
So our projections for warming.
Yeah, so the CO2 component, roughly speaking, the current amount that we have is creating a heating power density of 3 watt per meter squared, roughly speaking. And it turns out that the aerosol component, historically, before, say, the Clean Air Act, etc., has a range between 1 and 2 watt per meter squared. So it's roughly half of the thermal impact compared to the CO2 warming in the cooling direction. So if, say, we didn't know their existence to begin with, we would think, okay, CO2 is warming at 1.5 watt per meter squared rather than 3. Therefore, our future projections is based on a less detrimental heating component. But now, more and more we realize, the cooling component, which we are making every effort to get rid of, including the recent 2020 International Maritime Organization shipping fuel sulfur reduction to 0.5% by weight. As we clean them up, we are revealing the true heating potential of the CO2 and other greenhouse gases.
The full warming. Okay. So we're concealing the full warming effect of CO2 by polluting the air and getting this aerosol cooling effect. And as we clean up the air, we're going to have a greater warming effect from CO2. And our projections don't currently, like when you think about, or when you look at the IPCC projections, they don't currently take that cleaning of the air impact into account.
They do, partly. But some of the IPCC parts are very mysterious. For example, the special report on 1.5 degrees. So to make the point in that special report that the 1.5 was somehow still possible back in 2018, the authors of that section used the lowest possible estimate for the aerosol component of 0.7 watt per meter squared, whereas the central estimate given in the scientific component portion of the full report was 1.3. So there's some doctoring or cherry picking of data in producing some acceptable policy summary for the policymaker.
Yeah. Okay. So all that to say, you started really digging into the research and projections while you held this lab position at Harvard. And I'm gathering you realized things were more urgent and extreme than you had previously thought.
That's correct. But not the only thing, because one implication of this realization is that renewable energy can no longer be the solution, because the premise is that when you have stopped emitting CO2 and polluting the air, you could stop this warming. But the process of decarbonization is also a process of pollution reduction, aka unmasking of the full potential of the warming. And when I look around, all the other labs working on energy, they're working on tandem solar cells or perovskite solar cells or other more efficient way to do a certain energetic process, but they would not address this aerosol issue. So there wouldn't be anything to compensate for the loss of this cooling component. So that's another motivating factor. We need to do more than just renewable energy. I need to also make it clear that renewable energy is not the solution. It's another toolkit, just like what MEER is to help going into the next, hopefully sustainable civilization. But it's not a solution for global warming.
Yeah.
Because their implementation would lead to short-term warming of a magnitude that's most likely sufficient to collapse the civilization. If we look at what's happening this year, the level of floods and on every major continent, and imagine that times twice the temperature increase with an exponential consequence on extreme weather events.
Yeah. Yeah, it's almost like I feel like I see this in so many places when we try to address climate change is by solving one problem, you create another problem. So in this case, by transitioning to renewable energy, we're actually reducing this cooling effect of the pollution that dirty energy has.
And people are talking about this transition. I don't think, transition also implies that we are either keeping the current consumption level constant or even growing the total consumption at the same time. But rather, we shouldn't be talking about that, right? We should be talking about how do we fulfill essential energy needs more efficiently and really consider what are the most essential energies in a future that's compatible with the biophysical limits of this planet, especially because now the whole planet is becoming less productive as a result of the various climate and ocean acidification and plastic pollution stresses that were put onto it. So we cannot really expect the human enterprise, aka the total energy and the material consumption or flux, to continue to increase just by swapping out how you are producing this energy. And we have to remember that renewable energies in general carry much higher material price tag than petroleum and fossil fuel, right? Because you need much larger battery in weight compared to your stainless steel tank for the same energy density, or energy density is very much lower compared to the chemical form. So the material baggage is much larger for renewable. So there's nothing that's free, right? So it's always a trade-off in engineering. There's no absolute best.
Yeah. So you think we'll basically have to learn to live with less as a society, or adapt to living with less energy, total energy produced as a society. So, okay, you're seeing all of this. You're working on nanoparticle research that probably has a very indirect tie to addressing some of these problems, if any, I would guess. And you decided you needed to do something that more directly addressed the challenge. Is that right?
Yeah, that's right. And that's, I think, one of the conceptual links between the nano world and the climate change challenge.
Mm-hmm.
The most annoying part of global warming is that it's global, it's huge. And any solution, it may look good on paper, may be very efficient in the lab, but if you think about scaling them, oftentimes, 99% of the time, you realize, oh, we don't have enough titanium for this. No, we don't have enough platinum for this. We don't have enough of this material or that type of energy for this process. Oh, or we cannot produce this radioactive material at the rate that's needed to compensate for the warming. One way or another, like scale is the challenge. In the nano science field, including semiconductor manufacturing, you have this Moore's law, which is exponential increase in the density of transistors on the phone, which enables correspondingly more efficient operation and faster computation on a smaller footprint. So we're talking about energy efficiency, we're talking about efficiency in the material usage, right? By going small. And nano world, we talk about different dimensions. 0-dimensional materials like nanoparticles, or 2-dimensional surface like graphene. So, and by going to these small dimensions, we can really reduce the quantity of things. For example, if you consider, say, like 1 cubic meter of water, right? If you go to 1 centimeter thickness, then it's just 1% of the weight. If you go down to like 1 nanometer, then it becomes 1 billionth of a ton, which becomes a very small mass. In the case of something like a mirror, whether you mount a mirror on top of a whole building, or you have it freely suspending in air, from the top, it looks the same, because the function of this surface is just to reflect the light on the part above it. It doesn't really care about what's underneath. So the question is,
It's two-dimensional.
how thin can you make a mirror? It turns out that if you're using pure aluminum, you can go down to as thin as 15 or 20 nanometers, and you still get the full function of a more typical, say, hundreds of nanometer or 1 micron thick mirror. And the 15 nanometers is 15 billion of a meter. It's a very small.
So from the standpoint of just the sheer amount of material needed to have an impact or to scale, mirrors are effective because they can be so thin and still have the same impact.
Because we have essentially reduced a 3-dimensional problem of the Earth's atmosphere mixed with CO2 to a 2-dimensional problem of light reflection. So this dimensional reduction conceptually is what enables you to gain this efficiency relative, for example, the endeavor of direct air capture, in which case you have to filter through the entire 3D volume of the atmosphere. Whereas if you're doing a surface-based reflection, it's a 2-dimensional problem, which in the theoretical limit carries no thickness, hence a vanishingly small amount of material needed. And just to give you some concrete numbers, if we want to build enough mirrors to cancel the current emissions from each year, so roughly 50 gigaton of CO2, we need roughly 10% of the aluminum cans that the United States landfills. I think less than half of the aluminum, or roughly half of aluminum, is recycled. But a huge fraction are basically landfilled or just thrown away, not taken care of. So we just need a fraction of what's currently wasted in a single country to provide enough aluminum to produce the mirrors that we need. And right now we're testing different materials, including glass, but also PET, basically mylar, but the thicker grade of that, roughly 0.003 of an inch, 75 micrometers. And the amount of PET bottles, water bottles, that the world is throwing away every year is more than enough for us to make those mirrors to cancel the annual greenhouse gas emissions. So again, we have enough material.
Yeah, that's interesting. As opposed to like direct air capture, where I think the estimate I heard was we would need to redirect all renewable energy being generated in the world today, like our entire capacity for renewable energy, to get to the kind of gigaton scale removals with direct air capture that we're looking for.
Yeah, that's true. Yeah, both the material lens and the energy lens are important. So we have just covered or discussed the material lens for the specific of MEER. But in the process of thinking about these things, we also have developed a particular way and general way to look at all potential, quote, solutions from an energy point of view. The power that's driving global warming can be quantified. Just as if you are heating water on your stove, you can quantify how much heat is produced by the flame and how much is going into the kettle. So that can be measured. So the power that's driving the warming of Earth relative to pre-industrials is roughly 2,000 terawatts. That's 2,000 times 10 to the 12 watts, or 2 petawatts, 2 times 10 to the 15 watts. In comparison, humanity is using only 20 terawatts of primary energy. So that's the energy content of your fossil fuel combustion plus also renewable electricity. So in other words, the CO2 and greenhouse gas induced global warming problem is 100 times the size of the human energy procurement problem.
Okay, got it.
So the thermal energy driving Earth warming is 100 times the thermal energy humans create by burning fossil fuel in their cars, in their power plants.
So, which kind of suggests fighting that energy with energy is going to be a losing battle because our ability to generate is so far outweighs our ability to generate energy.
Unless you have a process which is ridiculously efficient, significantly more efficient than 100%, right? Because you have less energy to work with to deal with a much larger energetic problem. So there are examples in real life where that happens. For example, your air conditioner or your heat pump, which consumes
heat pumps,
say 1 kilowatt of electricity, but moves 3 to 4 kilowatts of thermal energy around, right? That gives you a ratio of 3 or 4, which is known as the coefficient of performance. But the challenge we have in front of us requires, at this zoomed out theoretical level, a coefficient of performance, COP, of 100. Yeah, because 2,000 terawatts of global warming power relative to pre-industrial is 100 times 20 terawatts, which humans consume. So 100 COP is the minimum if we did nothing but to use all the energy we burn to deal with the global warming problem, which is not realistic because humans, we have to do other things. We have to eat. We have to live our daily lives. Right? We have to do other things. So then what is a realistic percentage of the energy that we produce that can be diverted to fighting this externality? Well, we don't have theoretical model, but we can look at the empirical results. One of which is the relationship between how efficiently energy can be procured and how well a society or country does in terms of human development index, HDI. So it turns out that there's a very nice correlation between how easily a society produces energy and how well the citizens live. Roughly speaking, if you want a decent standard of living, the average of the pack currently in the globe, you want what's called the energy return on investment, EROI, for your energy source to be above 20. So in other words, you cannot use more than 5% of the energy you have produced to engage in activities for extracting that energy. So in other words, this activity such as energy extraction is an overhead for a human society. In the same way, in order to control global warming so that we can maintain a habitable environment, it's also another overhead. So by the same token, we cannot allow the addition of global warming fighting energy consumption to degrade the total effective EROI to be below 15 or so. So it's a small overhead we can add.
Right. That kind of gives us a budget to work with.
Correct.
Energy budget.
So globally speaking, if say everybody on Earth is okay with returning to a level of living, that's what's currently happening in North Africa, in Arab countries. So that's roughly middle of the pack. So Europeans, Americans, okay, tune down your standards, and Africans, we lift them up to that standard. If that's the goal for the future society, then we can use roughly 3% maximum of our current available primary energy for fighting global warming, 3%. So the implication of that is the theoretical ratio COP is 100. Then you have to divide that by 0.03. So that gives you a practical, feasible minimum COP for this global cooling AC system of 3,000.
3,000, yep.
Meaning every joule of energy you spend has to remove 3,000 joules, 3 kilojoules of energy from Earth system.
Okay.
And that's the minimum threshold for just conceptual feasibility. And that needs to be more broadly applied and understood for different solutions. So let's come back to the example of direct air capture. One can do that calculation. And that particular, what Climework does, for example, they achieve roughly COP of 150.
Oh, it's pretty good.
Which is roughly, it's pretty good, but it's 20 times short.
Not 3,000.
But it's not 3,000.
Yeah.
But it's 20 times short, which means, roughly speaking, 3% times 1020 is roughly half of the current energy sources, which roughly matches with your figure of the renewable energy production for CO2 capture. So that's the origin of that result, but viewed from a more fundamental perspective.
Okay. Can you explain at least the theory with MEER, but what's physically happening and how does that get us close? I assume close to this kind of 3,000 COP or a really attractive cooling return on investment.
Yes, you're asking about the conceptual underpinning of MEER.
Yeah.
So everything on Earth, the biosphere, including past geological processes, including the fossil fuels, the energy of that comes from the sun. Sunlight is at the most upstream end of all the processes, the flux of matter of energy on planet Earth, especially the biological system. So if you have a method that enables you to tune and optimize sunlight with high spatial resolution and temporal control, you in principle can control everything that happens downstream of that, which is all the meteorological processes, all the biological processes on planet Earth. And what we care most about as humans, selfish as we are, our habitats and the biosphere, most of which lives within 20 meters of the land surface and some maybe 50 to 200 meters of the ocean surface. So it's a very thin region of the vertical atmosphere and ocean. So out of all the different locations where you can perform this light reflection, surface of the planet is where you would have the most impact for the systems, the biology that we are interested in impacting. It's also the location where you have the most spatial resolution, meaning I can cool my house selectively without really bothering my neighbor, as long as my mirrors are pointed upward so that they can even see it. Whereas if you were to create a cloud by marine cloud brightening to cool your house, of course, your neighbor, your whole community, your city your province or state would feel the impact. So you lose this locational specificity, which generates all sorts of governance and policy issues on the side, but we digress. We're only talking about if your interest is to really provide the most intense localized cooling to protect your ecosystem that you care about, both in X, Y, and also in height, in Z. You wanted to do it at the surface because this is where most of the global biomass lives. So this is another fundamental reason why MEER-based solar radiation optimization could be most effective and selective and less intrusive overall. And then there is the ease of implementation. Well, it's a mature technology. MEERs have existed for thousands of years. We just haven't used them in this way. And humans are smart. We build all sorts of infrastructures. What's the challenge putting up a few MEERs? In about 4 years, with a small group, maybe 10, 20 people, we have developed many systems that are robust outside. They have survived the years of abuse, including hurricanes and snow in New Hampshire. They survived. So I think if a team of 20 humans can do that, imagine 10% of global scientists and engineers were attracted to this field, what kind of marvelous systems we can build. So I don't think the engineering is really a challenge. So that's the fundamental conceptual underpinning. And I'd like to talk maybe a little bit about local impacts. So what are the major ecosystemic stressors that our crops and trees and coral reefs are facing? Basically, there's too much light and it's too hot, and there's not enough water, or sometimes there's too much water. So let's look in turn how MEER locally implemented can solve or help to attenuate these stressors. When you block out the light, you create shade. And everybody knows how much cooler it can be underneath shade, especially in dry environments. So we've measured in New Hampshire soil temperature reduction at 10 centimeter depth up to 4 degrees Celsius, roughly 10 degrees Fahrenheit of cooling. And at the surface, if you extrapolate our depth measurement to the surface, is 10 degrees Celsius, 20 degrees Fahrenheit of cooling at the surface. And then let's look into the scientific literature on how freshwater usage for irrigation scales with temperature. It turns out that if you measure the transpiration rate from a piece of leaf and also measure its leaf surface temperature at the same time, the rate of water loss is exponential in the leaf surface temperature, especially in the range between 30 degrees and maybe 38 degrees Celsius. So one can achieve dramatic saving in irrigation water if you can reduce local temperatures by a couple of degrees.
Right. But help me understand this, because I think in my kind of mental model, what you're doing is putting MEERs on roofs. So you're cooling individual homes in a very kind of precise, localized way. Help me tie that to reduced temperature of water and other things in the ecosystem outside of those homes.
Okay. So sadly, there's not enough home, or happily for the other species and trees, we haven't encroached upon all of the land available.
Okay.
So humans, most of the land that we have transformed into our territory are for agriculture, cropland and also forage cropland, which covers roughly a third of global landmass. And the rest, like roads and roofs, those are a minute fraction in cities as well. They're roughly only 1% of what's required by the MEER framework to have a global impact. So we're doing some work in the urban environment to cool down, because that's where you can save people's lives immediately. And also you can show people how it's a easy and safe technology. So there's an educational component. So yeah, we do perform some experiments and work in the urban environment, but it's not where most of the implementation would be in the future.
Okay. So it's straightforward to me to understand putting this reflective material on a roof. How does this apply, and how that would cool the home? How would this be applied in these more natural environments or agricultural environments?
Well, let's talk about cooling of homes. No matter what you are trying to cool, there's two things you can do. Either you reduce the heat flux into the material or the space, or you increase the heat flux out of the space or this material. So during the day, the direction of the heat flux, if you take the net flux, is from the outside into the room. That's why things get hot during the day, because sunlight is converting into heat, both on the surfaces of the building, but also of the air, which then, through convection, will go into the building as well. So during the day, you want to cool, you want to stop heat generation at the surface. so there's less heat into the building. At night, if you want to cool, you better have methods that encourage the escape of heat from inside to the outside of the building, because sky becomes cooler at night, there's no sun, no radiation. So how you cool, basically, less in, more out. And during the day, the major component is a sun-induced surface heating. So if you reduce how much heat is converted into heat by increasing what's called albedo, by increasing the reflectivity, sunlight reflectivity of your building surface, then you reduce that component of heat load. That's how you cool during the day.
And that makes sense to me. You put a mirror on a roof, you're reflecting the sunlight, and you're reducing that heat into the home. What do you do outside of homes? You're talking about doing this to cool soil temperatures and water temperatures and plants. How do mirrors apply in that kind of ecosystem? Because you don't kind of have this structure to put a mirror on.
Yeah, correct. So for the roof, it's very convenient. You have myriads of different solutions. You can glue the film onto corrugated iron. We are also developing a method to suspend this film under tension across different attachment points. That's been very successful as well. So it's basically like a shading, outdoor shades. And those outdoor shades can also be applied over crop fields, which we also have built Protect for. They're pretty robust in width as well. And there's also possibility to take them, to roll them out of the way or stack them. We're currently trying to design different engineering systems that enable the deployment on demand of these systems using just one linear degree of actuation, but controlling like hundreds of meters of a linear mirror array.
Like a retractable awning made out of reflective material.
That's folding, self-folding, and we can stack everything into a garage, and then when needed, you can take everything out.
Yeah, okay.
That's the current working prototype for agriculture. For reservoirs, so before going into these details, I want to come back to just name a few numbers so people have a better understanding of the scales involved. We have three major application areas now that we're pursuing. One is the urban cooling. The other is to save water of freshwater reservoirs. And the third is to cool agricultural land, shield crops from excessive sunlight damage. The ratio of these are roughly 110 to 1. So 1% of the area is roughly the roofs, and 10% are freshwater reservoirs, and then most of it are actually to be deployed over crop fields. That's just a consequence of the natural ratio of the areas on land we are using for our lives. We're using a small portion for our dwellings, a slightly larger for water storage and capture, and most of it to grow crops. So they conveniently become different by one order of magnitude each.
Okay.
We talked about one way to deploy over agriculture. Over water, you have different options depending on the size of your water storage pond. For like the individual family farmers with a small pond, maybe an acre or half an acre, I don't know, maybe 50 yards on the side, you can certainly deploy the same system, suspended system, compared to agriculture. Just awning type on highly tensioned stainless steel cable rails. That's feasible. On much larger systems, you have to do something similar to floating PV, but using materials that are less heavy, because PV panels are very, very heavy. This mirror material we have is very, very light. 1 square meter is only a few tenths of grams. So it's essentially weightless. So you require very much lighter floating infrastructure. And in Freetown, we did a very cool prototype based on PET bottles from this bottled water. And we can make such systems that has an area of 1.5 meters, and we have tested them in the ocean for several weeks, and they're robust. So it's a system composed of 100% trash directly using just simple processing steps, and you can make floating mirrors that's stable and survive the ocean. So we believe such system, when we introduce a few more precision machining techniques such as injection molding, would enable us to produce directly usable systems for freshwater reservoirs.
Yeah. What has been the reception in Sierra Leone? I think it's interesting because you have some actual families and households you're deploying your mirrors on. I'm curious to hear how that has gone and what people think about it.
We have been able to help about 50 households so far. All the people are very happy with the product. And the problem we have are with people who weren't chosen in the first phase because they see their neighbors enjoying a very cool environment. And when our team going into the community to do work, collect data, sometimes they are treated with the passive aggression or other issues because people are complaining why it's still not their turn because it's been a year. So the problem is that people want it as soon as possible. But obviously, we are small, nonprofit, we're limited by our bandwidth. So the reception by the end user so far in the urban case is overwhelmingly positive, a bit beyond our expectations, and it's actually creating some minor annoyances.
Interesting.
Because we cannot supply at speed.
Can you quantify what kind of change in comfort they're having? Like, what does it do to their in-house temperatures relative to their neighbors?
Yeah, we have running sensors, time series, in all of these and other households. And if you look at the distribution of temperature and humidity over the past year, 2023, 2024, during the heat season, from March to May, roughly speaking, those conditions is outright deadly for people above 65 years of age. So imagine finding yourself at 60 to 80% relative humidity, and the temperature inside these houses are 42 degrees Celsius. I think well over 100 Fahrenheit. Maybe you can do a big conversion.
Yeah, 107.
107 and 70, 80% relative humidity.
Yeah, yikes.
So, and we are able to, reduce that by 15 roughly degree Fahrenheit, 7 degrees Celsius during the heat of the day. So temperature would be returned to 35 degrees Celsius. And that's much more survivable.
Yeah, at least under 95 degrees. Yeah.
It's survivable, but it's not ideal for functioning.
Right.
But at least the people don't risk dying just by virtue of sitting in their house.
In their homes. Mm-hmm.
Yeah, in their homes. And our next phase is to ask the question, what if you increased the aerial coverage? Instead of single structure, single building, what if a whole community were covered with these like materials? Whether there's any additive benefit effect, which we suspect to be the case, because when you have your neighbors experiencing the heat, that through the wall, there's got to be some through the wall conduction loss of the cooling impact. So we could have another couple of degrees of added thermal comfort when this is scaled.
Right. What's your ambition for MEER? What kind of impact do you think MEER can have on the world?
Well, to be honest, if something like MEER, some form of direct cooling local adaptation is not applied, it's unlikely for global agriculture to stay healthy for much longer. If we look at agricultural projection papers, the likelihood of concerted global crop failure in the next 10 years is significantly higher than 10%. So there is a very high chance that we'll be seeing concerted multi-breadbasket failure, crop failure in the not too distant future. And the main stressors are, again, high temperature and low soil moisture. And both of these conditions, MEER field can help to attenuate, reducing the temperature and also keep the soil moist longer. I think by necessity, it's almost inevitable that something like MEER will get used, even as some users may not even know that a concept, a overall conceptual framework already exists for their application.
Yeah. Is MEER ever going to scale to a point where it could have an impact on the global temperature rise, or is it more about just local impacts?
We have done the analysis for global impact from two perspectives. One is a more like top-down, to look at the current energy balance on land, the global land surfaces, and like how much sunlight you can receive and how much a meter squared or foot squared of MEER can reflect, and how many of those you need to have a global temperature impact. So from the top-down analysis and also bottom-up, based on some computational papers that ask similar questions. For example, if you brightened the color of the leaves of crops by, say, 10%, what's the temperature impact globally?
Oh, interesting.
So from these two global top-down perspective and also crop land use change perspective, we arrived at a consistent number. That is, if you cover roughly 1% of the Earth's surface area, you can reduce global average surface temperature by 1 degree Celsius.
Oh, wow. Okay.
And 1% of the global surface area is huge, mind you.
Yeah.
That's roughly 10% of the global agricultural land.
Okay.
That means we need to cover, if you have 1 acre, you should devote 1/10 of the acre to maybe dig a pond and float MEERs on it. So that's one way to satisfy your personal contribution as a farmer.
Okay.
As a hobby farmer. Yeah. Or you use some shading that covers 10% of the surface area. So 10% is strewn over your field. So that's another way to do your bit. So I think realistically speaking, the absolute upper end that we can do without negative impact on global agricultural productivity is roughly 5% of the global surface area. That's the absolute upper end, meaning the total global cooling potential of the framework using only agriculture and freshwater reservoirs is about 5 degrees Celsius global average cooling. But I don't think it will ever scale that big.
That's massive.
That's massive.
Yeah.
So I think realistically, on the order of 1% to 2%, so 1 to 2 degree global average temperature reduction is entirely feasible and actually necessary in many cases, because otherwise nothing would grow. Your soil would become barren. It's like a necessity, something that would naturally emerge.
Okay. I want to make sure I understand your perspective on one thing. Do you believe we should also in parallel be investing as a society in renewable energy and, I don't know, carbon removal and some of these emissions mitigations, moving to all the electrification and all of this kind of stuff? Are those worthy investments?
Renewable energy, most definitely.
Okay.
Though we have to re-examine how we use that energy. Is it really wise to use electric cars? Why can't you just use electric bikes, everybody?
Yeah.
And these things called the velomobiles, which are essentially enclosed bicycles that are lightweight. So those are by far the most efficient land transportation system because they're lightweight and they're fast. The speed record by humans without electrical assistance is well over 100 kilometers per hour, close to 100 miles per hour on a highway using these enclosed bicycles, because the fairing really cuts down all the aerodynamic drag, which is where the dissipation comes from.
Yeah, we should be electrifying. We should be moving to renewable energy. Those are worthy investments in solar and wind and geothermal and all of this. But we also need to be finding ways to use a lot less energy as a society. I ask everyone these last 3 questions. How optimistic or pessimistic are you about the future of the planet and why?
Planet Earth will be just fine. They will forget about us in a few million, tens of million years, because mammalian species only stick around for like a couple million years anyways. And even if we have a mass extinction, life will evolve again. All the biological processes will happen again, and the planet will be just fine. So, and there's nothing to be worried about.
Fair point. I like that answer. Who is another individual or company doing something to address climate change that's inspiring you?
So, well, I guess it's a bit of conflict of interest, but we're starting to collaborate with Reflective Earth, which is trying to help quantify and monitor the cooling impact of these surface-based installations. And I think their work is very important and also go hand in hand with our actual installation. We're trying to collaborate to better understand and quantify and follow the impact of individual person who adopts the approach.
Cool. Reflective Earth. I'll look them up. What advice do you have for someone who's not working in climate today but wants to do something to help?
Learn gardening, because before you know it, you'll have to grow your own food, and teach us with your best techniques, then we can work together to grow more efficiently.
Okay, sorry. Just say a little bit more about that. Why do we have to learn how to grow our own food before we know it?
Oh, well, the current agriculture is based on running these heavy machineries that depends on fossil fuel, petroleum to be specific. And also there's all this fertilizer manufacturing system that depends, the distribution and manufacture of which depends on these resources. So it's inevitable that food prices will go up, not the least of which is because of this resource depletion in a healthy running human system, but also climate stressors. So we need to think about how to secure our own food. That's one way to think about it.
Yeah, it's been really fascinating talking with you. I've learned a lot, and I really appreciate your ability to kind of recognize the urgency and severity of the challenge, but still work tirelessly on a toolkit that'll help us get through it as best as possible. So thanks a lot for your time. Appreciate it.
Thank you. You're doing the same thing, so thank you.
Hardware to Save a Planet is brought to you by Synapse. To find out more about us and how we develop hardware solutions for the world's most ambitious companies, head to synapse.com. And then make sure to search for Hardware to Save a Planet in Apple Podcasts, Spotify, and Google Podcasts, or anywhere you like to listen. Make sure to click subscribe so you don't miss any future episodes. On behalf of the team here at Synapse, thanks for listening.